Hello friends. Let's explore the I/O features of the Aries 3.0 development board further. In this video, I have shown how you could read an analog input using the onboard A to D converter. First, let us just read a voltage connected to the analog input pin A0. I have used a jumper wire to connect the onboard 3.3 volt power pin to the analog input connector pin A0. In the Arduino IDE, open voltage example sketch from the ADC example menu as shown. The sketch is a simple one. It reads the analog voltage signal on the A0 pin of the Aries 3.0 board. I have defined an additional variable ADC reading. The resolution of the ADC is 0.002 volt or 2 millivolts. In the setup function, the serial port is initialized with the baud rate as shown. In the loop function, the A to D converter channel A0 is read and stored in the variable ADC reading. The read voltage value is computed by multiplying the ADC reading with the resolution to millivolts. In the following section of the sketch, both the voltage value and the content of the ADC reading variable are printed on the serial port. The same task is repeated every 1 second. I already compiled and uploaded the sketch and connected to the serial monitor. I am getting 3.28 volts and the corresponding ADC reading 1639 or 1640. If you are wondering where the A to D converter is located on the board, take a look at the bottom side. You will find this tiny 10-pin IC. I could not find any details about the ADC in the documentation for the Aries 3.0 board. Therefore, I did a bit of reverse engineering to learn about the device. From its marking on the package, ADS 1015 seems to be the A to D converter from Texas Instrument that is used on this board. This is a 12-bit Sigma Delta ADC. The ADC has 4 channels and the digital interface is I to C. Therefore, it can be made out that the port pins A0, A1, A2 and A3 are connected to the input channels of the ADC. The processor accesses this device using the I to C interface. The information on the full-scale range could be found in the datasheet of ADS 1015. The resolution in the example code we saw earlier is mentioned as 2 millivolts. As per the table, the corresponding range for the ADC is plus or minus 4.096 volts. I am not sure about the negative input range, but certainly 0 to 4.096 volt range with a 2 millivolt resolution is supported. As mentioned in the datasheet, never apply more than the VDD plus 0.3 volts to the analog input channels, because that might damage the ADC. Let us now connect the Grove light sensor module to one of the analog input pins of the Aries development board. And let's read the analog voltage from the light sensor. I am using the latest sensor, which replaces the LDR with a phototransistor as shown. The phototransistor is a linear light sensor device. You could explore the datasheet to learn more. A piece of useful information can be found in the application schematic diagram and the equation presented in the datasheet. As more light falls on the phototransistor, the current through it increases and the voltage drop across the 10K resistor increases. Therefore, the voltage across the resistor is proportional to the light falling on the photosensor. Next, I connected the photosensor module to the Aries 3.0 board. Connected the VCC signal of the Grove sensor to a 3.3V port pin. Tied both ground connections of the sensor and the Aries board together. The voltage signal is connected to the analog channel A0. For testing the sensor, I have used the LDR sensor example sketch. The sketch reads the analog signal on the pin A0 and drives the green LED on if the value read is greater than 1200. Also, the value of the red analog signal is printed on the serial port. I have commented on a couple of lines in this code, which are not necessary. After I compiled the sketch and uploaded the same to the Aries board, I am reading a value of 1007. As the light is allowed to fall on the photo sensor, I read a maximum value of 1007. Considering 2 millivolts as the resolution as explained earlier, this value corresponds to a voltage of 2.0 volts. Also observed that if the light sensor is guarded using a piece of paper to prevent light from falling on the sensor, the count reduces. Also, verified the voltage from the sensor is actually 2.0 volts using a multimeter to double check. Let me conclude this video here. Thanks for watching. Hope you will join me back in my next video.